We pick up our discussion of the sampling distribution of X bar by taking a look at an example. We know that the mean of the sampling distribution of X bar is mu. We know that the standard deviation of the sampling distribution of X bar is sigma divided by the square root of n. And we know for large sample sizes that the sampling distribution of X bar is approximately normal. So in this case, as we saw in our last video, we know that the mean of the sampling distribution of X bar, let's see if I can spell it out here. Let's see how my mu sub X bar is equal to the population mean, which is 12.05. We know the standard deviation of the sampling distribution of X bar is equal to the population standard deviation divided by the square root of n, which is going to be the square root of 100. So in this case, it's 0.0025. See if I can squeeze it in. And we know, because in this example, we have 100 sodas. We're interested in the sampling distribution of X bar. We want to find the probability that the average soda amount in the sample, the average, it's an X bar problem. So when I look at this statement now, before we were doing normal work, we were working with X's. Now we're working with X bar. So I'm going to label this as an X bar. But the way we approach it is very, very similar. I'm going to take the 12.045 and see where it falls relative to the mean. Well, 12.045 falls over here, falls below the mean. So I'm going to draw it over here. And what do we want? We want the probability above. We want the probability the soda amount, the average soda amount exceeds. So we want an upper tail probability, which, as we know from working with normals in the past, our tables work with cumulative probabilities. The way we're going to be able to solve this is by taking 1 minus the lower probability. So you have a couple options here. One option, as we saw with normals, is we can change this thing to a z-score. Figure out what the z-score is for 12.045. So I take 12.045, I subtract off the mean of 12.05, and then I divide by the standard deviation over the square root n, the 0.0025 number, and I'd get a z-score of -2. I could look up the z-score of -2 in the z-table, and it would give me this lower probability here, and then I would subtract that lower probability from 1. And we saw how to do that when we were working with the normals in an earlier section, but we also found is that Excel offers, and I'll just, oops, there we go. Excel offers a really easy way to find normal probabilities without going through the z-distribution. Because the Excel function, the norm.dist function that we saw earlier, allows us to use different values of mu and sigma, we plug in the values of mu and sigma, except notice what I'm doing this time. I'm putting in the value that I'm interested in. I want to learn about the probability surrounding the value 12.045. But the mean and the standard deviation for the 12.045, I'm using the mean of the sampling distribution of X bar, which is the same as mu. But this is where you have the difference. I'm using the standard deviation of the sampling distribution of X bar, which is sigma over the square root of n, in this case 0.0025. I always put true here. We're always looking for cumulative probability, so we always put true, and that's going to give me this function here. The norm dist, this part here, is going to give me the less than or equal to probability, the lower tail. That's why we subtract it from 1, because we want an upper tail in this case. When we do that, that's the value that we get from the Excel function. That's also the value we get in our z-table if we looked up the cumulative probability for a z-value of -2, which is what the 12.045 is. So you got both options. You can change it to a standard normal and use a cumulative z-table, or an easier option, in my opinion, is to use the normal distribution function in Excel and just plug in the right values for mu and sigma. We take it and subtract it from 1 again because we want a greater than probability. Let's take a look at another problem. As I'm going through doing normal problems with you, I'm trying to plug in gaps. I'm like, what did I miss? What haven't I shown them yet? There's one thing left. Suppose Coca-Cola has a pouring machine that dispenses soda into 12-ounce cans. Same problem. Machine has a mean with a 12.05, standard deviation of 0.025. Suppose 100 sodas are randomly sampled. Same exact type of problem. And it actually looks like a similar problem. Find the probability that the average soda amount in the sample is less than 12.07. So again, I'll put in the mean at 12.05. This time, a couple things. The 12.07 falls over here on the right because it's above 12. Whoops. 12.05, so I'm going to put the 12.07 over here. And then the other piece is I'm looking less than, so I'm going to shade less than. So I'm going to shade this lower tail, which is the cumulative probability we can find from the table or from the normal distribution function. Now, the thing that's different about this is, sorry about my little announcements coming in here, my team's announcements. The other difference here is that if you go the old route and calculate a z-score for this, if you take 12.07 and subtract 12.05 and then divide by the standard deviation of 0.0025, the sigma subscripted with x bar, you get a z-score of 8. Wow, someone's having fun on Teams. You get a z-score of positive 8. That's the z-score if you were to go and look it up in the table. And if you go to your z-table, you're not even going to find it there. If you were doing this the old z-table route, you're going to be like, wait a second, it's not on the table. And that's because all the probability falls below positive 8. And so what you would find if you went to, all right, this is getting annoying now. If you went to the z-table, most z-tables stop at like 3.5 because there's no probability beyond that. So what we're going to say is when the z-score falls off the table, the tail probability beyond it is approximately 0, and so our answer is going to be approximately 1. Now, if you go the XL route, which is the route that I'm suggesting, you're going to use the normal distribution function. You're going to put in 12.07, you're going to put 12.05 in as the mean, 0.0025 as the standard deviation of the sampling distribution of x bar, comma, true, and you're going to get an answer that's 0.9999999999999. It's huge. It's approximately 1. Anytime you see more than 4 nines, when you see a 0.99999, it's going to be approximately 1. When you see a 0.000000002, we're going to say approximately 0. We're going to round to 4 decimal places. So a lot of times when you're working with the sampling distribution of x bar, we get z-scores that are crazy like this. We get values that are way off the chart, so to speak. And so it's not uncommon to see an answer of approximately 0 or approximately 1. Doesn't mean you have to, but it's not uncommon that you will. Okay, this problem was new, not because it's a less than problem, not because it's a normal problem. It's new because it was a problem for the first time where the value I ask about falls so far out in the tail that the answer is either approximately 0 or approximately 1. Now, in this case, it's approximately 1. What if I change it around? What if there was another version of this question that said, find the probability the average soda amount in the sample is greater than 12.07 ounces? Well, that's a greater than. We would do 1 minus this, and the answer would be approximately 0. So that's how we work with the sampling distribution of x bar. All right, I got one more question for you, a couple parts to it. The interest rate charged on revolving credit card debt follows a normal distribution with a mean of 18% and a standard deviation of 2%. Find the probability, and really what I want to do in this problem, I want to check out the wording here. Now look what I'm asking. Find the probability a randomly selected credit card has an interest rate that exceeds 20%. I'm going to have a very similar question in part B. If you have your notes printed, you already see it. But here's where we're at. We've seen normal problems. We've seen normal problems when you're working with populations of x's. Now with the central limit theorem, we also see normal problems working with the sampling distribution of x bar. So solving normals, as you guys have seen, is a very similar process. If you like using the z-table, you can solve them both using the z-table. If you like using the normal distribution function in Excel, again, my preference, you can solve them both using that. You just use a different standard deviation. And so the question that you really have to ask yourself when you figure out, oh, this is a normal problem, because most people are going to look at this and you're going to draw this picture. You're going to draw the picture that has the mean of 18%. Let me back that up. Sorry. You're going to put a value of 20 over here, and you're going to shade greater than. You're going to get that part right. But the question I have for you, when you draw this picture, is this an X or is this an X bar problem? And how do you know? Now you can see here in your notes I've written it as an X, but it'd be really easy for me to put a bar over it. How do you know? We know we have a normal distribution, that's fine. We got 18, we got 20, we got the greater, but how do you know? Well, there's 2 ways that I can ask questions. They're both going to deal with credit cards. They're both going to deal with individual values. Find the probability of a randomly selected credit card. That's one, that's an X. The other way I could ask this question, find the proportion of credit cards. Those are the X's. What's the probability of randomly selected one exceeds 20%? What's the proportion of all that exceed 20%? Those are both X's. To be an X-bar problem, you have to take a sample from the population. You have to be looking at a sample mean or a sample average. Take a look at the wording in an X problem for that. But here, in order to solve this, if I was going the old score route, I would do the z-score, but I would do the X version of the z-score, which looks like that. X minus mu over sigma. When I do that, the z-score for this 20 in the X version becomes a positive 1. And so I look at the probability that the z-score exceeds 1. So I look up the positive 1. I'd see 0.8413 in the table, and I'd subtract it from 1. Or again, you guys know that while that works, it's fairly straightforward just doing it this way. Notice what I'm doing. I'm putting in the value of 20. That's the value. That's the interest rate that I'm interested in. Putting in the value of mu and sigma that apply to the x's. And then I'm putting true. And when I get that, I'm going to get a value of 0.8413. I'm going to get the same exact number here from the normal distribution function that I get in my table. And I still need to know to subtract it from 1 to get my answer. That's what the X problems looks like, which of course leads to the question, well, what's the X bar question look like? Here you go. Suppose we randomly sample 100 credit cards, find the probability that the average interest rate of the sample exceeds 20%. So I still have a picture that looks like this. I still have a value of 20 out here, except now, look, I have a sample of size 100, and I'm interested in an average. The other word I could use here would be the mean interest rate. This is an X bar. Now, I've told you all along, I don't care if you draw these things to scale. The main thing you want is to get the pieces set up on the correct size. 20 is bigger than 18, so I'm going to throw it to the right. However, this problem is much, much, much different than the last problem. When I was working with the x's, the z-score that we used was x minus mu over sigma. When I use the X bars, I'm still subtracting the mean. That doesn't change. But what changes here is the denominator. The z-score for the value 20, and the last problem it was a value positive 1. Here's a z-score of positive 10. That falls way out in the tail. And so you would go and try to find 10 in the table. You're like, it's not there. And that's because the probability less than or equal to 10 is approximately 1. The probability further out in the tail is approximately 0. We're trying to figure out the probability X bar exceeds 20. Now, when I go to my norm dist function, I put in the value of 20 as the number that I'm interested in, except now, when I plug in values of the mean and the standard deviation, I'm using the values for X bar. And you're going to get a value of 0. The norm dist function is going to return a value of 1. When you subtract it from 1, you would think it's equal to 0, but it's never really equal to 0 because this curve never really touches down in theory. So whenever you get answers of 0 or 1 in normal distributions, we always say they're approximately 0 or approximately 1. And so that's the X bar version. What I want to try to do, and this is going to be sketchy, so have some grace here. Here's what I want to try to end with. No, I want to end with a picture. And of course, the picture that I'm going to want to use is going to try to put both those parts on the same picture. And of course, with this pen and the way it freaks out, here's the X version. We had a normal curve. This is the interest rates. Had a normal curve that was centered at 18. There are my X's. And the standard deviation was 2. And so 1 standard deviation above the mean would be here, maybe at 20. 2 standard deviations of the mean would be here. 3 standard deviations would be out here. And so here's 20. And what I was looking for is the probability X is greater than 20. And that's the probability. We found that was 0.1587. That's what we did in part A. All right, let me change colors here. This is the picture that's going to be maybe a little bit more challenged. Let's go to a nice blue here. So then in part, the next part, part B, we were working with the sampling distribution of X bar, which was still a normal curve, which is still centered at 18, except now the standard deviation isn't 2. It's 2 over the square root of, and sample size was 100. The standard deviation was 0.2. And so now when you think about drawing a normal curve, here's what we know about normal curves. The area under the curve is 1. Most of that probability is between plus and minus 3 standard deviations. So when the standard deviation was 2, this would be maybe 24 And if I go 3 standard deviations in the other direction, let's see, 16, here's 14, this would be like 12. So most of the interest rates, most of the x's would be between 12 and 24. Well, when I have a standard deviation of x bar that's equal to, let's see if I can draw a line over there, here we go. When it's equal to 0.2, 3 standard deviations is 0.6. So most of the observations are going to fall between 18.6, which is maybe about there, and 17.4. So I'm going to draw a normal curve where most of the probability, this is the x bar normal curve, most of the probability is between 17.4 and 18.6. So I'm drawing a normal curve that's really tall and skinny. This is really tough to do with the stinking mouse I have. And so I'm trying to draw a normal curve that's got an area of 1 that has most of the probability between 17.4, 3 standard deviations below the mean, and 18.6, 3 standard deviations above the mean. And it's not tall enough, and it's not, I need more probability in the x bar distribution. But the point is, when I come out here and look at a value of 20 in the x bar distribution, you're like, hey, there's nothing out there. There's no probability beyond 20 in the x bar distribution. And that's what we said right here. When you take a sample, as a sample size, that's what I want, as the sample size increases, these sampling distributions get taller and skinnier and taller and skinnier. And here's where we're going. Here's where we end up. In a discussion I'm going to have with you very, very soon. Okay, maybe the next thing you look at, maybe the next module, maybe the next time we come back to class, however you're getting this material, in a discussion we're going to have very, very soon, we're going to turn it around. I'm going to tell you, I'm going to let the cat out of the bag, which is a terrible expression, by the way, but I'm going to tell you, what we've been doing has been kind of fake. We've been looking at binomials where I'm assuming we know the probability of success. We've been looking at normals where I'm assuming we know the value of the mean and the standard deviation. Spoiler alert, we usually don't know those values. I don't know mu, I don't know sigma, but somebody wants to know. I want to know the average interest rate of all credit cards. I want to know the average interest rate of all home loans. I want to know mu, I want to know sigma, I want to know the population proportion pay. I want to know those values. And so what we're doing, what we're going to do, is we're going to take a sample and try to estimate those values. And so here's what we're going to do. We're going to take a sample and we're going to calculate a value of x bar. Now we know the value of x bar that we're working with is going to come from this distribution right here. And so what we're going to try to do is get a value of x bar, and typically we won't know this number here. In this problem I told you it was 18%, but in general it's some unknown value mu. We're going to choose a value from this sampling distribution and hope we get pretty close to the population mean. That's that inferential technique I talked about a while ago. We're going to take a sample, we're going to calculate values from that sample, and we're going to use them to estimate unknown population parameters. And we want to do it accurately. And what we're learning here in this chapter is that as you take bigger and bigger sample sizes, the standard deviation gets smaller and smaller. In other words, this distribution I'm drawing gets taller and skinnier around the value mu. What that means in our future is, as that distribution gets taller and skinnier, our estimation gets more accurate. We're going to be able to take the sample information and more accurately predict or estimate the value of the population mean as our sample size gets larger. Now, those are some ideas, some thoughts for the next time we get together. For right now, you need to understand what a sampling distribution is. You need to be able to work with the sampling distribution of x bar. You need to know the three things: the mean of the sampling distribution of x bar, the standard deviation of the sampling distribution of x bar, and the shape, and then be able to work some probability problems with x bars. Ultimately, it's going to probably end up in an Excel spreadsheet using some normal.dist functions. So now it's your turn. It's time for you to get to work. When you have questions, reach out to us. We'll be glad to help. So long.